Hallo und herzlich willkommen hier auf der Stage 2. Ich freue mich sehr, Rosa Menkman ankündigen zu dürfen und würde auch gleich das Wort an Sie weitergeben. Wir hören jetzt einen sehr spannenden Input-Talk über die künstlerische Forschung in der Praxis. Viel Spaß dabei.
My name is Rosa Menkman. Thank you, Merlin, for your introduction. And I also want to thank Fabian Roth for inviting me, the whole team of HoloLabs. I only know Anne-Katrien Lipke from name, but thank you very much. I was asked to give a presentation about how the sciences can interact with the arts and vice versa. And I have, I think, kind of a love-hate relationship with this particular interaction. And I wanted to share some of my, well, first of all, my oldest story, which is what you can see here. It's a diary entry from 1993. So that's already 30 years ago, somewhat. In my diary, I write in Dutch because I'm actually from the Netherlands. I'm writing, I have found out what I want to become. Something with gymnastics, or I would love to go to space and find new sounds. And what happened is when I tried to find out the ways to get to space and find new sounds, my teacher kind of smashed my dream, telling me, look, Rosa, there are no sounds in space, so forget about it. And that's kind of the first time this imagination kind of got squashed, and the scientific perspective, or the kind of the institution that I was inside, kind of broke my imagination. I have I've worked in university institutions for almost 2 decades. And in 2006, I actually graduated with a master thesis on Jody. And here, Jody is a Dutch and Belgian art collective. This is an old work by them. It's called Untitled Game. I wrote my master thesis about it. And in Untitled Game, Jody modifies Quake, first-person shooter. And so what you get is like these glitchy environments in which you can like play around, but you can't see if you can win or not. So it's more like a visual tool. And I really love this way of work, but while I was writing about it, I never felt like I could really understand it. So what I tried to do is kind of remake the stuff that they made. I started to explore in a more practical way to understand what was really happening. And at this time, the word glitch was not really incorporated yet as a figure of speech, or even in the artistic scientific domain. So I kind of tried to understand it, but without that understanding of glitch art, as it later became known, it was kind of really hard. So while doing kind of like interpretations on what Jody did to Untitled Game, I started also working with other types of file formats. So not just like the video game format, but really on a very static level, like images. And that's how I created a vernacular file formats. And in the vernacular file formats, I kind of put a glitch in the code of the image. And by then kind of like looking at what comes to the surface, you can kind of see the aesthetic organization of that code of the file format. So you basically see the language of that file format. This is the original video from which I took the image of a vernacular file format. This is me like 12 years ago, so I was a little younger. So here you see me taking like the source image, and then you get all these different types of most used file formats, like a BMP and a GIF and a Targa and a PSD, a JPEG and PNG, the JPEG 2000, the Photoshop format, and also the Targa format. What I learned from this way of working is that while we use codes inside our computer as kind of like a system that functions in one way, code itself can actually, or data itself can actually be much more fluidly used. And that's what I started to describe as Rheology of Data. So you can kind of like push data through different ways of reading. And actually what I started to realize is that while you push this type of data through different ways of reading, you kind of get to explore all kinds of stuff. You can explore, for instance, the sound of a rainbow. I kind of like demonstrate that here in a very basic rainbow, but you could take any image of a rainbow and sonify it. And what you would hear are like the gradients, the differences between the colors and how they change over. That is something that kind of like gives you a new access to understanding information or data and finding new information out of that data. And that understanding kind of initiated what I call resolution studies. On my website, I break up resolution studies in 5 different topics: materiality, genealogy, habit, institutions, and scale. But I think after now doing resolution studies for quite some years, I'd say there might be some more categories, but this is how my studies and the writing about this has been explored on my site. I define resolutions not just as a way to make things function, but also as a compromise. So if you make one thing function in one way, like you listen or you look at the rainbow, you compromise kind of the ability to listen to that rainbow also. And so one of the most important things, or the ways I have come to understand resolution studies, is also the searching for what is compromised in our modes of operation, in our computational processes, etc. So I'm trying to find ways to break with the condition of not considering these compromises. And with that research in 2019, I kind of reformulated as a study into shadow knowledge. I said, like, I wrote a proposal to CERN about exploring the shadows of knowledge, because I think that in these kind of places, these compromises that are kind of like still lingering on the limits of what is possible, we can find new kinds of information. So with that proposal, shadow knowledge, in 2019, I won the Collide Barcelona International Award. And that was really beautiful. I spent a few months. CERN is just to show it here, like, it's the biggest experiment in the world. It's a particle physics institute. And basically they shoot particles through this ring, and in 4 places, 4 main places, because there's also a couple of smaller places, they do experiments. They have the events where the particles collide and they kind of abstract knowledge from that. So what you get with this residency is the chance to talk to different scientists. And one thing I immediately learned from being there is that when I came there, I am not a physicist. So I had to kind of start to learn the language of the institute. But at the same time, the way I do my research, in this case, shadow knowledge, was not really the way the scientists in CERN do their research. Now, one thing I did learn is that I'm talking about the scientists, but there is no such thing as the scientists. Every scientist has their own way of working. And I started to kind of organize myself, like looking into what was their field of research, or what was their type of research, let's say. So if you have a mathematical particle physics scientist, then they have a very different way of approaching research and conversation about that research than when it's someone that works more in like the philosophical part of particle physics. And so all these scientists, they have their own way of conversating. And I started to have to kind of change my way of talking once I knew who I was going to talk to. The problem was that I came with a research that was called shadow knowledge, which is kind of a metaphoric concept. And people inside CERN, they don't really talk in metaphors. So that was one of my main problems. I needed to change the research I was doing. And so I had to kind of reformulate the research of shadow knowledge into kind of a new research question. And so I sat down with my scientific advisors and we rewrote the question. And so this became a research that is titled Impossible Images. So once you come to CERN, they set up appointments with different scientists. And I think all in total, I had about 50 to 60 conversations with different types of particle physicists. And every time I started with one question, the same question, and that was this question. Imagine you could obtain an impossible image of any object or phenomenon that you think is important, with no limits on spatial, temporal, energy, signal to noise, or cost resolutions. What image would you create? So just to make it a little bit shorter and simpler, imagine you could obtain an impossible image. What image would you create? And so from asking all these scientists the same question, I kind of got this like huge collection of impossible images. I just want to mention one of my favorite answers. This is one by Harrison Prosper. We spoke about my wish from 1993, where I wanted to go to space and listen to new sounds. And he said, look, when I go with my daughter and look at the sky, one thing I always try to tell her is that when you look at the night sky, you actually listen to the ongoing reverberations of the Big Bang. So you're listening to the loudest sound that ever was, or you're looking at the largest, loudest sound that ever was in this universe. So actually he brought back my dream. So finally I started to collect all these answers and kind of try to organize them. And one thing that I realized is I needed a way to kind of get through these impossible images. I needed to make a strategy to understand them. And one of them was writing a new formula about where the impossible image space exists. So this is what I did while I was in Barcelona, because one part is at CERN, the other part is in Barcelona in my case. And I met with the Institute for, what's it called? Sciences del Cosmos, the research of the cosmologies. And there they also work with, for instance, the Magic Telescope. And I talked to one of the scientists, Xavier Lurie, and we started to formulate this kind of concept that there is a messenger that goes through a window, and then through a transform, we finally get the latent image. So in analog photography, the latent image space exists when photosensitive materials have exposed a material, but that material has not yet gone through the process of development. So it's a kind of a space that has been touched by the light, but that is not showing its trace evidence yet. It's this space that can be developed through these different kinds of transforms. When I was talking to the scientists, they all work with different types of experiments. And so they also all use different types of objects. Like they could use photons, they could use electrons, they could use gamma rays. Those gamma rays, they need to be kind of picked, or they have to touch an object. And that's the window. And in this case, with the gamma rays, it's the Magic Telescope. And that information has to go through a transform to become finally a latent image. So that understanding I wanted to capture all the different kinds of impossible images I had collected with the conversations of the scientists, I wanted to capture and explain them in an artwork, and that became the blob. Here you see the blob. In the blob, I used this concept of the latent image as more of a hypothetical space that involved every imaginable or unimaginable image that could ever be rendered. So a main premise of the blob is that once a render parameter is chosen, so a render parameter are these transforms here, the parameter kind of acts as a metaphoric cut through the latent image space. So it cuts, it kind of makes a resolution, it resolves the image, but it also compromises other stuff. So it divides the space up, and what remains possible becomes an image, and then there's also the impossible image space. So effectively, every render setting also kind of involves a compromise. So this formula became kind of a formula to capture what also gets compromised. It became a tool for me to talk about compromises. I just briefly want to show, oh, this should play. Let's see if it plays. It's a video. Maybe it's too heavy. Otherwise, I can break out of the presentation mode. I guess we have to do that. Because I want to show the blob. I think it's an important example. There we are. Oh, he really doesn't want to play. Then we just move on because we can't wait for the videos. The blob is online. It's visible. You can actually find it by just using your phone and go through this QR, and then you can download it and you can take a hike through the impossible blob of images. I made this blob during the pandemic when all galleries were closed. But then when restrictions started to change, I was invited by Lothringer Dreizehn in Munich to actually actualize this virtual blob into a real space. So I started to transpose the blob into this huge old building. So I had all these impossible images, and I wanted to not kind of bombard the audience with all these different concepts. So what I did is I started to categorize them, and I abstracted 5 main categories of impossible images. And so these are the 5 ones: images based on speculation, disbelief, or imagination; low fidelity images; chronologies of impossibility; all possible images and new complexities; and humanly unreadable images. And while this blob that I previously tried to show, but that is this virtual reality space, or this 3D space that you can navigate through and find all these impossible images online, I wanted to kind of translate that idea of axes that cut through space that I could really easily show in this virtual space to this real space in the Lothringer. And so what we decided was really directly break the space through lines. So this is the exhibition. These are a few of the images. Gonna try one more time. This video luckily works. This is how you come to the space. It's the really big poster outside. This is a video I made real quick, but it's me entering the Lothringer, and then you see immediately this like white axis, which is the axis of all possible images. And then you can follow that axis, and then the axis gets cut by different types of, oh, here is the blob, the virtual blob that was also at the entrance of the exhibition. And then you have these like red line here, which is the axis of low fidelity images, with a few works. This is a work by UCMV about Marais. and another work by Peter Edwards. And so we can walk through the whole thing, but I just wanted to kind of pick out a few of the images or the works in this exhibition that I thought were really special. I mean, they were all special, but that I think work best in a presentation mode. This is a work by Fabian Heller. It's called All Possible Images, True Color, Full HD. If you look at it, it's basically this sheet of paper that moves with the y-axis of all possible images through the space. And Fabian here basically calculated the number of all possible images on his full HD screen. Fabian is a student of mine, and I asked all my students to consider impossible images and maybe make a work about them. Actually, the only student that finally did do that was Fabian, but I really loved this work because this is all, as you can see in this image, there are all these little numbers, and all these little numbers, they add up to one giant number, and that is the calculation of every image he could ever display on his display. So that image could contain my slideshow right now. It could be a photo or an image of your grandmother. It's like all the possible images that could ever be shown on that display. And so it's a giant number. It's 1920 times 1080 that are the amount of monochrome images, and then that number times the amount of colors that this display, which is 24K, can show. And so it's this unspeakable number that he printed out. But what it stands for is every possible iteration between 0 and that number, and that is every image that could ever be shown. And the nice thing about that image of all possible images is actually that it's an impossible concept for humans. We have no number for this. Like, we cannot actually pronounce this number. We can also not humanly fathom it, because in a lifetime we would not be able to see all those images. The other part of the story is that actually to calculate this number wasn't easy at all. Like, a calculator won't churn out this number because it will just give you like 10-digit basically with some like letters. So to actually get to a way to calculate that is you need to write a special program for that. Then what you get is a text document, but that text document is basically too heavy to open for most computers. And then you have to print that number. And there are very few printers that actually know how to deal with such a number. So the number of all possible images itself became kind of like impossible to cope with. Another example is this work by UCNV about moire, which is basically some images, some parameters by which images are originally created are often no longer supported by the image processing technologies that want to try to show them. So this can happen when, for instance, an encoding system has become unsupported or doesn't support the amount of pixels of the image, because it's either higher than the resolution of the display, or the computer just doesn't know the protocol to process them anymore. So when that happens, and that happens in mostly older codecs these days, the technology or the decoder has to try to interpret that data. And so as a result, the carrier that tries to translate the signal to an image will also influence and kind of deform what is finally being displayed. In this video installation by UCNV, it was really beautiful because you saw 4 states of the same kind of image data, which is this line fabric. So you have the original PNG, you have the PNG as a cloth, a flag, and then you had 2 videos in which 2 ladies were carrying this fabric, one in full HD and one that was compressed so small that the lines of the fabric couldn't fit into the image anymore. And so then you get this like supercritical state in which it becomes kind of organic fluid. This is the work by Pete Edwards that I already showed. this is the blue line. This is Chronologies of Impossibility category. And here I basically collected 3 images that have different timestamps of impossibility. So what you see here in the back is a Röntgen photo. Röntgen images or X-ray photos, they were once impossible until Wilhelm Röntgen kind of invented this technology. Another example of impossibility is an image that was once possible, but that has now become impossible. And this is the pale blue dot. She's hanging here. It's a photo from the Voyager. The Voyager is this satellite that was sent to space to kind of explore what is outside our galaxy. And Carl Sagan asked NASA to take one last photo before the Earth got too small to be photographed. And so what you see is basically here you see the Milky Way. In the middle there's this little dot that is just 1 pixel. And that is the Earth before the Earth became smaller than a pixel and could no longer be photographed. So this was the last photo that was possible before Voyager, the image of Earth for Voyager's cameras became too small and was no longer possible to capture. This is the green line, and this green axis represents images based on speculation, disbelief, or imagination. This axis had 3 works on it. Here, right now, you see work by, or a quote from Ingrid Brington, "Forever noon on a cloudless day." And with that quote, she refers to this base map of planet Earth, which is kind of the way we understand Earth, right? But this image is actually inaccurate, and it is also full of bias. So what you see is the Earth being having no clouds. It's noon everywhere, and all the land masses are stretched. So it's a very doctored image. It's an image that we have like included in our belief of how we see the Earth, but it's not how the Earth is actually existing. There was a few other works that I really love in the green line. This was a work by Open Weather. Open Weather also gave a workshop during the Impossible Images Research Week. And in this workshop, we listened to the NOAA satellites. And the NOAA satellites are the weather satellites by the US. And they send the information that the satellite sees from up, they send it straight to us. So if you use an antenna and you focus on the right frequency, you can capture that data and actually see what the satellite sees from up. And so we learn to dial into these satellites. And then you see all the noise that comes with these images, and that the way we normally look at the weather and the images from the sky that people make their weather reports from, they're actually not so real, as they're very kind of clean, whereas the reports that we see by these satellites, these NOAA satellites, they're much more full of noise. The final axis is the yellow axis, which was titled New Complexities and Humanly Unreadable Images. It's too complex now to talk about, but this is the axis that also involved machine learning algorithms. So it had works by Memo Acton, Alan Warburton, and myself. And finally, which is where I will leave this presentation, there was also the workshop area where I invite people to give me their concepts of impossible images. So the collection of impossible images is still growing, and we're now working on a catalog of the show, but the submissions are always open, and I think there are many more impossible images and so compromises to catch out there. So that's still my mission. Thank you.
Thank you very, very much, Rosa. It was such an interesting presentation about artistic research. I love your work and your approach. And I want to invite you to the talk launch 2 on Gather to meet the audience for questions. Thank you very much.